And then we got when at 0, so those are the three equations there towards the bottom. So we have y of 0 equals u1 0 plus u2 0 plus u3 0 equals 0. Then y prime of 0 is u1 prime of 0 minus 2 u prime of 0 plus 3 u3 prime of 0 is minus 4. This is what we have from our question from the linearly independent solutions. And then we have for y double prime of 0, we have u double prime 0 plus 4 u double prime 2 of 0 plus 9 u the third u double prime of 0 equals 14. And then all we needed to do was to so now this is where it's new. So the black pen is what I want to use last time, and the blue pen is what I use this time. So all we need to do was work out the equations to solve the equations here. So I used matrix, and I got reduced row echelon form to get U1 to get the three C's, C1, C2, and C3, the three C's that come after the Y's, the U's, sorry. So I got C1 equals minus 3, C2 equals 2, and C3 equals 1. And so that comes out to our, I mean U's, I think. And that comes out to Y equals minus 3 e to the x plus 2 e to the minus 2x plus e to the 3x. Yeah, I mean U's, sorry.
It's okay. Yeah, sometimes we use too many variables. We
Yeah.
forgot to use one. Yeah, the book stays with C's. Yeah, you
Right.
can use U's. Yeah, just be consistent. All right,
Right.
that's very clear. Thank you, Albert.
Thank you.
Thank you. Then I think next one is Yaprak, right? You also want to fix from last time.
Yeah.
Okay. Okay, what about the rest of you while waiting for Yaprak?
Okay, so I presented this question last class, but I couldn't finish it properly. But now, like, I wrote it in detail, like how I came to the conclusion. So first, I also provided here the theorem that we need to use. So that's that. I'm not going to repeat it because we all know. But second of all, I verify if y1 and y2 are linearly independent by computing the Wronskian. And from the last class, we remember that I didn't get 0, so they turn out to be linearly independent because Wronskian was equal to 0. And then I assumed their solutions, despite the question being stated that they're not, so that, like, if there are the solutions, then y1 and y2 would satisfy the differential equation given. So, like the one I highlighted here, like the general solution. So I substituted the general solution to the given differential equation. And then from there, we would choose C1, C2, P of t, and Q of t in such a way that the equation, this equation, would hold true. But observing the derivatives and the, like, y sub 1 and y sub 2, we see that, like, they have different forms and, like, they behave differently. Like, there's no proportionality between the functions. So it means we can't find a proper values to make that equation, this big equation, to be true. So it means they're not solutions indeed to the given differential equation.
Nice. Nice. Good fix. Very nice. Thank you.
Thank you.
All right. Okay, let's start with anyone want to present 9.1? We'll just go down the list. Oh, Anqi, right? Anqi is 9.1. Yeah, go ahead, Anqi.
Can I share? Let me see. Am I? Oh, I am a presenter.
Have I presented?
Yes, I'm sharing
Yes.
now. There we go. So I am doing question 9.1, which is find the general solution to the differential equation. And we can see here that we're giving an nth order homogeneous linear equation. I'll enlarge this. There we go. So the question is y double prime plus 8y prime plus 16y equals to 0. So first you want to find the characteristic equation. So how I think of it is, I know this is not exactly the right logic, but if I see double prime, I think that as like to the power of 2. If I see 1 prime, to the power of 1. If I see no prime, that's like y to the power of 0. Or sorry, r to the power of 0. So following that logic to get the characteristic equation, I got r squared plus 8r plus 16 equals to 0. So the point of doing this is we're trying to see if this characteristic equation has a real root. And if it has a real root, then based on the theorem described in 9.1 here, we can find a general solution to the differential equation. So like I said before, for the differential equation, the characteristic equation is r squared plus 8r plus 16 equals 0. That factor into r plus 4 squared equal to 0. So your r equals to -4. And because this is a repeated root, you have to remember to put an extra x. It's not just c1 times e 4 to the x plus c2 times e to the 4 to the x. It has to be c1 e times 4 to the x plus c2 times x, because again, it's a repeated root, and it's twice repeated. That's why you only put 1x here. If it were 3 times repeated, let's say we have a root of r1, r2, r3 all equals to -4, then you would put plus c3 x squared e to the 4x.
Anqi, do you mean, yeah, Anqi, do you mean e to the -4x?
-4x, because the root is -4. I apologize.
That's right. That's okay.
I rolled it wrong.
Okay. Yeah, because this is from lecture 9. If any one of you have any questions, yeah, feel free to jump in to ask any questions. All right. Okay. Thank you, Anqi. Yeah.
Thank you.
So 9.2 is 9.2. Suxian 9.2. Yeah.
Yes, I am.
Okay.
Oh, sorry. Oh, you can see it, right?
It's on the way.
Yeah, so my screen can see. How about you, everybody?
Not yet.
Oh, not yet?
Yes, now. Yes.
Okay. All right. Today I'm presenting 9.2. That's like equation is y double pi plus 4 y pi plus 20y equals 0. This is a homogeneous equation, as we know. So I start with the left substitution. So y is equal something. So I skip everything. And then now we get a characteristic equation is r power 2 plus 4r plus 20 equals 0. So this one we cannot figure out, and then the root. So I use the dramatic formula. Is R equal next B plus, and then the power B, no, square root B power 2 minus 4 AC. I plus in all of them is equal 4 plus and minus power root 16 negative 80 over 2. This is like when like a 16 minus 80, like a power root is become like a negative. That is not real number. So the rule is not real number. So we always come in the conjugate pairs in this case. So like we get like R1 equal 2 plus 4i, and R2 is equal to minus 4i. I like A equal 2 and B is equal 4. So I write like this way, R1 and R2. This is like a new things for real, not non-real rules. So when they come like this, have the theorems like this. If the characteristic equation has a pair of complex like a conjugate rules, A plus ABI, then the corresponding pair of the generation of homogeneous equation is like a Y equal EAX times C1 cosine BX plus C2 times sine BX. So I plug in, get the like a general solution is Y equal E2X times C1 cosine 4X plus C2 sine 4X. That's my solution. Thank you.
Okay, that's for plus, right? But you still have A minus BI. You have 2 minus 4i.
Oh.
You left a half part. Okay, I'll let you go back to check, but I'm going to talk about this later, okay?
Oh, okay. Thank you. Thank you.
You're
Let
welcome.
me check. Thanks. Thank you.
Thank you. All right, let's see. Who's 9.3? Anybody present 9.3?
No, I will.
Okay. Oh, Moses, okay.
Can you see it?
Not yet. I still see Shuxian's work up. Let me see if I can.
Oh.
You should have a button to I don't know why it doesn't give me the button to close this. Shuxian, can you close your screen from your end? Somehow I don't have my button appear now. Usually I get the button to close one's work. Okay, now, yes, that's yours, right?
Yep.
Yeah, 9.3, yes.
Yes. So we need to find the general solution of y third prime plus 3y to the second prime. And we know that it's a real solution, meaning we don't have to do the complex stuff. So to get the characteristic equation, just like in 9.1, I kind of just replace depending on what the differential number is, I replace it with the exponent. So my original equation would go into r to the third plus 3r to the second equals 0. And then we factor out r squared, meaning we now have a double root of r equals to 0 and then r equals to negative 3. So because we have a double root for r equals to 0, we need to have a c1 plus c2x times e to the 0 times x plus c3 times e to the negative 3x. And because we know that e to the 0 is equal to 1, meaning we can our final answer would be y equals to c1 plus c2x plus c3e to the negative 3x.
Okay, yeah. All right, thank you. If
Thank you.
anyone has any question, feel free to jump in. So that's 9.3, 9.4. Anyone has? Yeah, Muhammad, go ahead.
Can you hear me?
Yes.
Awesome. Let me just share my screen. Give me one moment. So, all right. Can you see my screen?
It's probably popping up, but now still black.
Give me one moment. Do you see it now? I just fixed it.
Not yet, but it says you are sharing content.
I'm sharing content. Give me one moment.
Oh, yes, now.
All right.
Yeah.
So for this problem we have y so y prime, and we got so we got this right here, and we want to find the characteristics equation. So this will be r to the 4th plus 6r squared plus 9. So we factor it out and we get r squared plus 3 for both, and then so when we get r squared plus 3, so this will be an imaginary number, because since it's plus 3, it's going to be an imaginary number. So it'll be plus minus 3, square root of 3, the imaginary. And for our case, what's going to happen is we're going to have like this, where we're going to have like cosine and sine right here. We have the C1 and C2, and then we have the x right here as well. And we'll have like cosine square root of 3x plus x C4 sine square root of 3x. I went a little bit quick on this one. I'm still confused about it myself. So yeah. Yeah.
Okay, I'm going to talk about it later.
Yeah.
I see that.
Yeah.
I see that, even you guys can do your work. Okay, that's okay. We're going to learn. Shuxian, you have questions?
Yeah, because I checked your example, you only have the negative, like y equal like 2 something, so that's why I skipped like a negative thing, b.
Yeah, I see that.
Yeah,
That's okay.
because I read your sample, so that's why I confused too, but I just try my best. I'm so sorry.
No, that's okay. That's okay. That's perfectly fine. Yeah, I just want to, mention it. So, yeah, so I'm going to talk about them, so not to worry.
All right, thank you.
You're welcome. All right, so that's 9.4. So 9.5. David has 5. David, hope you can explain thoroughly. I'll just try it.
Oh, okay. So the problem is to find the general solution of the given differential equation. And here we kind of use a similar method to what we learned last lesson. We just substitute in e to the rx. And here I kind of skipped that step because I'd done a bunch of other ones, so it was kind of just a given. I'm sorry if that's confusing. But in other words, what you end up having is you factor out the e to the rx, then here you end up with, that's not a negative, that's just a piece of eraser on r to the 4th. So r to the 4th plus 2r to the 3rd minus 3r squared. You do some factoring, and then you find out that your roots are -3, 0, and 1, where r equals 0 is a root of order 2. And this means that we have to use a different series for repeating roots, where it's basically the formula is ck e to the k minus 1 times e to the rx. And so because we have two roots, we have c1 plus c2x, and then outside of that, in the parentheses, we have e to the 0 because the root is r equals 0 to the x. And then the rest is like as we normally do, plus c3 e to the negative 3x plus c4 e to the x. And then you can simplify by simply just making e to the 0x equal 1, because anything to the 0 power is 1. I forgot to add an x after C2. So yeah, that's a mistake. So it's C1 plus C2x plus C3 e to the negative 3x plus C4 e to the x. Okay.
Great. Yeah, you just miss x for C2. Yeah. All right. So that's point what? I forgot. 5. So now 6. Anyone? Liz. Liz has 6.
Yes. I'm doing question 6, which asks to solve the initial value problem. I have y double prime plus 4y prime plus 13y equals to 0. Y0 is 2, y prime of 0 is 5. So we're going to replace a y by e exponent or x. Y prime going to be or e exponent or x, and y double prime going to be or square e exponent or x. So now that we have those new value for y prime, and y double prime, we substitute that into the original equation that we had. So it's become or square e exponent or x plus 4 or e exponent or x plus 13 e exponent or x equals to 0. We factor by e exponent or x, and since we know that cannot be equals to 0, so it must be a squared plus 4r plus 13 equals to 0. So now we're going to try to find R1 and R2. So when we apply the formula, we find out that it's not a square root of like a positive number. So we're going to have to use some imaginary numbers. So R1 will be negative 2 plus 3i, and R2 will be negative 2 minus 3i. The characteristic equation has a pair of complex conjugate roots in the form of a plus or minus bi. So the general solution gonna be in the form of y equals to e ax times c1 cos bx plus c2 sine bx. In our case, a is negative 2 and b is 3. So we're gonna go ahead and replace a and b into the general solution. So y equals to e exponent negative 2x times c1 cos 3x plus c2 sine 3x. So now we're gonna go ahead and try to find a particular solution. So we know what y prime of 0 is. So we're gonna look for y prime and then equals what we find to the value that they give us, which is 5. So when I y prime, which we know is the derivative of y, so I kind of consider y as a u times v function, and the derivative will be u prime v plus v prime u, where u
Liz? Liz? Can I hear you? Liz, we lost you.
So now that I have this, I make it equals to 5. I replace y prime of 0 by 5, and I replace x by 0. And then when I simplify, it's give me 5 equals to 3c2 minus 2c1. It's because like sine of 0 will be 0 and the cos of 0 will be just 1. And I also replace for y of 0. So I know y of 0 equals to 2. So I go back in the general solution that I had. I replace y by 2 and I replace x by 0. So I end up with 2 equals to C1. So I called 5 equals to 3, C2 minus 2, C1, like equation 1. So I'm going to go ahead and replace my value of C1 into this particular equation that I had. And when I solve, I find that C2 is equals to 1/3. Now that I have the value for C1 and C2, I can just replace them so I can find my particular solution. So y is equals to e exponent negative 2x times 2 cos 3x plus 1/3 sine 3x.
All right, thank you, Liz. Katerina, question 7.
Yeah, give me a second. Let me share. Tell me if you can see it or not, or it's still loading.
Okay, probably, yes, now.
Yes, you can see it. Okay, perfect. So
Yeah.
we have 2y to the third prime minus y to the double prime minus y prime equals 0. And then we have y of 0 equals 9, y of prime of 0 equals 1, and y double prime of 0 equals 4. So we start by solving the characteristic equation, and we get 2r to the third power minus r to the second power minus r equals to 0. I decided to factor out the r, and we get this equation. And then going on from here, I decided to do a quadratic formula. So I assigned the letters. This would be our A, this would be our B, and this would be our C. So I plugged it in, as you can see here, and I got I got 1 plus or minus 3 divided by 4. It should be an I here, I'm missing it here since it's an imaginary number. And then, so we find our roots, and since we...
Hold on a second, that's complex roots? I see you have a square root of 9.
Yeah, but isn't it plus or minus?
Yeah, but these are real roots. You don't have
Yes.
complex roots.
Yes.
Complex roots means under square root, you have negative number, right?
Yes, that's what I meant. Thanks. Thank you.
Yeah, you have real roots.
Yes, I have a real root. So since we factored this r out, this r equals to 0. And then since we have plus or minus, so we take it as here as a minus, so it would be 1 minus 3 over 4, which simplifies to negative 1 over 2. And then if we take it as a plus, it would be 1 plus 3 over 4, which simplifies to 1. So from here, we start by finding out the general solution, which would be y equals c1 e to the power of 0x plus c2 e to the power of x plus c3 e to the power of negative 1 over 2x. So since e to the power of 0 is just 1, we just simplify it to this c1 plus c2 e to the power of x plus c3 to the power of negative 1 over 2x.
No, I think you're missing e. No, C3.
Oh, yeah, I'm missing an e. Yeah, you're right. You're right. Yeah, I am. So from here, considering here would be an e, which I'm missing, we find the derivative of it, and we get y prime. C2 to the power of ex stays the same. C1, since just a constant, it just cancels out. And then from here, we just bring negative 1 over 2 to the front, and then we get C2 e to the x minus 1/2 e to the negative x over 2 C3. From here, I took y double prime, C2 e to the x stays the same, and then from here we multiply negative 1 over 2 to here, which will gives us a positive 1 over 4 e to the power of negative x over 2 C3. Going to our initial conditions, which is y of 0 equals 9. So we plug it into our general solution, which will give us 9 equals c1 plus c2 e to the power of 0 plus c3 to the power of 0 as well. And this just as 9 plus c1 plus c2 plus c3. And then moving on to the next general solution, y of prime of 0 equals 1. So we use our y prime equation. We plug in the numbers. So it would equal to 1, c2 to the power e to the power of 0 minus 1 over 2 e to the power of 0 c3. E to the 0 is 1, so we just have 1 equals c2 minus 1 over 2 c3. And our last initial condition is y double prime of 0 equals 4. We take our y double prime, and once again, we just plug in the numbers, and we would get 4 equals c2 e to the power of 0 plus 1 over 4 e to the power of 0 c3. Once again, e to the power of 0 is just 1, so we would just have 4 equals to c2 plus 1 over 4 c3. From here on, I use the system of equations to find our constants. And so I used this equation and this equation because there are 2 unknowns in each. And I subtracted them, and I would get -3 equals to -3 over 4 c3. And then to get a value of c3, you just multiply both sides by -4 over 3. And we find that our c3 is 4. And then I use this equation up here, and I plug in my c3 in there, which will give me 1 equals c2 minus 1 over 2 times 4. And this would give us our second constant, which is c2 equals 3. And then I use this equation right here, the first one, and I plug in c3 and c2 into it, and it would give us 9 equals c1 plus 4, and this would give us a constant of c1 equals 2. So coming back to our general solution, which is right here, I just rewrote it. It's y equals c1 plus c2 e to the power of x plus c3 e to the power of -1 over 2x, and we just plug in our constant that we just found, which would give us y equals 2 plus 3 e to the power of x plus 4 e to the power of -1 over 2x. And that's it.
Great. Thank you.
Thank you.
Thank you. Thank you. That's a 7, right?
Yes.
Okay, so 8, 音频 8. Then we'll have a rhyme for 9. Then Christian finishes up your own version of 9. Can't hear you. Yingping, are you talking? Yeah, I can hear very, very low voice. Yeah, maybe raise your volume, voice volume. No, I can hear you, but a very, very low voice. Okay, so she give up. Maybe later. Okay, let's have Ryan first. Ryan.
So my question is somewhat the same as the other ones, but a bit more interesting. So we are given one of these solutions, and we are asked to find the general solution. So y triple prime plus 4y double prime plus y prime minus 26y equals 0. And that's our differential equation. And since we're given y equals e to the 2x, we know that one of the roots must be r equals 2. And so converting the differential equation into a polynomial, as we've done before, we can basically take the root out by dividing, and so we can solve for the remaining function. So I just did some polynomial division. R minus 2 goes into r cubed plus 4r squared, r squared times, you subtract that, then you have your remainder, you repeat over and over again. There's no remainder, so we just have r squared plus 6r plus 13. Then that's not easily factorable. So using the quadratic formula, we have a negative discriminant. And so that means that we have we have two imaginary roots. So we basically pull the negative out. We have the I, square root of 16 is just 4. And so we have negative 6 plus or minus 4i over 2. That simplifies to 2 roots, negative 3 plus or minus 2i. Now, as per the notes, and what other people have presented, for complex roots a plus or minus bi, our solution is of the form e to the ax times constant 1 times cosine of vx plus constant 2 times sine of vx. And I believe that does handle both the roots. The solution does seem to work. And so I basically just plugged it in. So our a here is negative 3. So we're going to have 2e to the negative 3x is. And our b is just 2. And so we have cosine of 2x and sine of 2x. Of course, we still have to include e to the 2x. And we weren't told if there's a constant multiple of that. So it's just e to the 2x. And the two constants are right there.
Okay, you also do not include the minus 1. You have negative 3 plus 2i, you have negative 3 minus 2i.
Oh,
that's okay.
I think I know what you're talking about. In the notes, it says that we're only interested in the real roots of this. So not the or rather the real solution to the differential equation, not the imaginary one.
Oh, I see.
Otherwise, that's why we would put the negative.
Okay, got you. All right. Okay. All right. Thank you, Ryan. Okay, last one, I think is Christian.
Okay, putting it up right now. Okay, you see it?
Coming up.
Okay.
Yes. Oh, very neat.
Okay, so I did a version of question 9 for this chapter, similar to Ryan's, and the question is as follows: y is equal to e to the power of 5x is one solution to y to the third derivative of y minus 7 minus 7y double prime plus 20y prime minus 50y is equal to 0. Find the general solution. I basically just found a cubic function that would give me 2 imaginary roots and 1 real root, similar to question 9. And I solved it by first step stating that y is equal to e to the rx, and then from then on you can see that the derivatives are going to eventually like expand from r e to the rx and so on. And then the second step that I did was I factored out e to the rx, and then I have my oh my god, my function, the function that's
You don't have function? You do not have function here? What are you talking about?
r to the third. Well, not function,
Equation.
sorry, expression or equation 0. Okay, I did synthetic division, which is on par with what Ryan did with polynomial division. It's the same concept. I knew that 5 was a solution for my r, not only because it's implied heavily by the fact that y is equal to e to the power of 5x, but because if I were to find the factors of 50 and I were to plug in one of those factors, which is 5, I get 0. Therefore, 5 is a solution to r, the equation right there with terms r. I do synthetic division. I get my coefficients are 1, -2, 10, and then 0 for the end. It's going to be 1 degree lower, so I just put the coefficients in front of r squared. That's going to be correlated to 1, and so on and so forth. I have this equation right here. Then I use the quadratic formula. It's pretty straightforward. I get a discriminant that's negative. Therefore, I have a pair of conjugates, which is going to be 1 plus 7i and 1 minus 7i. And then I'm going to place in my values into a general solution form, which for this expression, it's going to have 3 constants, and your real solution is going to be isolated right here with C1 5x, and then your imaginary solution, the real part of your complex number, which is okay, the imaginary part of your complex number is going to be right here. The real solution, which is 5, r is equal to 5, is going to be right here. Sorry. But yeah, that's your answer.
All right, very neat.
Mhm.
Okay. All right, anyone has any question? Or anyone else like to present? Okay, for some of you, you need to prepare to present, right? Like Bishin, Israel, Kyle, Marcus, Ronald, Rosa, Shan, Silo, Suzanne, and Zihao, okay? Try to present. You see presentation, it's, again, if the homework does not have enough questions, you can always make up your own questions, just like a Christian did. You can just pick a homework number, you make up your own homework, right? You see Ryan present 9, right? 9 has e to the 2x with a certain equation. And Christian made up e to the 5x, right, with an equation. You can always do that, okay? Okay, so anyone has any, I know last class I was cut off. I was talking to myself the whole time for the later part of lecture 8, which is a higher order linear differential equations. Anybody has any question over this lecture? If not, I'm gonna go ahead to talk about 9. But what's important for this lecture is the 2 roots. We separate, we know we could have finite many roots, right? But we separate with 2 kinds. Yeah, let me just mention that. important part for this. Yeah, let's just go over a little bit. So we call this nth order linear differential equation, right? What is it? We say y to the nth prime, y to the n minus 1, so on and so forth, y double prime, y prime, and the y. Then with a function of x. So all of the coefficients of the primes are function of x, right? Because this makes up nth order differential equation. Okay. And if this, well, this we just want to make a nice format, right? If this one not equal to 0, if the leading term, the leading coefficient is not 0, we can divide every term by the leading coefficient to get this form. Then if this f of x equals to 0, which means we do not have a function of x all by itself in the equation, and we get a homogeneous equation, which is nice to deal with, which, we can find a function, we can find solutions to it. Because this is a higher order, this is the nth order, so how do we deal with it? We separate it into two parts of the solutions. And of course, we still can apply Wronskians to check if the solutions are linearly independent. So basically we have this. So we don't use y1, y2, y3. So we use yp. All right. So this yp means a particular solution, right? Just one single particular solution. Because nth order we could have n at most n solutions. So we just pick one. We call we call yp, right? Basically one particular solution, and all the rest of the solutions we use the complementary. We call yc. Okay, so this is a key feature of this. Then yeah, should I go over one example? Anyone wants to see one example? Well, we're okay with this one. Anyone has any questions? Okay, let's go over one. Let's see this one, right? So let's see, we have one particular solution, and this solution is x squared plus 1. Is to the equation. This is the second order differential equations. Well, y double prime, y prime, we have y, and we have function of x. A function of x, right? So this is not 0, right? If this is 0, if it's a homogeneous, we can use the method for homogeneous equations. Since this is not homogeneous, we're going to use the one I was just talking about. So we want to find the solutions. We want to find a particular solution to this differential equation with these two initial conditions. Because this is a second order differential equation. If we want to solve for one particular solution, we need two initial conditions. We need one point from y. We need 1 point from y prime. All right. If this is a third order, we would need 3 initial conditions. We would need 1 for y, 1 point for y, 1 point for y prime, and 1 point for y double prime, so on and so forth. So first, we have this one particular solution, x squared plus 1, and we want to find the complementary solutions, right? So what do we do, right? we set this one equal to 0, right? Homogeneous equation. So the characteristic equation is this. Remember, this is e to the rx, right? E to the rx. So we have r squared plus r minus 2 equals 0, and this is effectable. This is effectable, so we get two solutions for this equation, 1 and -2. And that tells us the complementary solution. The complementary solution is C1 e to the 1x, right? Because r is 1, e to the 1x, that's e to the x, plus C2 e to the -2x. So that's complementary solution, right? C1 e to the 1x plus C2 e to the -2x. So the general solution to this non-homogeneous equation is the sum of the complementary solutions and the one particular solution. So we just add them together. Okay. So this is one particular solution. This is complementary solutions. Add them together. Then so take first derivative. We get this. We plug in initial conditions. We have y of 0 equals to 5. Plug in. We get C1 plus C2 plus 1 equals to 5. Plug in the second initial condition for y prime. We get C1 minus 2C2 equals 1. So we have these two variables with two equations, guaranteed solvable. So we solve the system of these two linear equations. We get a C1 equals 1, C1 equals 3, C2 equals 1. So we plug back into the general solution. So we get this. So this is a particular solution, this is a unique solution for this second order differential equation with two initial conditions of such. Okay, anyone has any question? Yes, Shu Xian.
Can you repeat what the YP represent?
YP just means one particular solution.
Oh, okay. So I know the YC is the complex equation. So, okay, I got you. Thank you.
YC means the complementary. So we have, imagine this. Imagine we have nth order of differential equations, right? Because this is just for y to the second, this second level.
Okay.
So we could have at most n solutions. So we just pick one and we call it particular solution. And then the rest of it is YC, because the rest of it is complementary to this particular one. Just means the rest of it. All right, any other questions?
YP is a particular solution. Okay. Y.
So should I talk one more example? Anyone like to see one more example or feel okay with this? All right, if we are feeling okay with this, let's go to lecture 9. By the way, you guys did a great job today. Thank you. You know, for professors, once you teach a couple of years, especially over 10 years. Okay, anyway. Homogeneous equation with constant coefficients. Okay, remember before the coefficients could be function of x. Like, you know, constant coefficients is still, you know, function of x is just constant functions, right? So this is just one special situation. So solve nth order homogeneous linear differential equation with constant coefficients. So right now, instead of we have, you know, p of x, right? Pn of x. So all those ones as just constants. Before we have all those ones a function of x, right? So this is one special situation. Again, we'll work with this. We work with one solution e to the rx, all right, rx. So we know the first derivative will be r times e to the rx. Second derivative will be r squared e to the rx. Nth order derivative will be rn r to the nth e to the rx, right? So we get this. So the r to the nth, all those r's, right, become part of the constant coefficient. Right. Factor out e to the rx. So we have a polynomial equation. Right? We have an nth order polynomial equation. So we don't solve this polynomial equation. In this, because why we call characteristic equation, because this is a part of finding the solutions for this differential equation. So that's why it gets a special name, characteristic equation. But in general, this is just a polynomial equation. Theorem. If the roots of the characteristic equation are distinct, means different, right? Are distinct, real numbers. So we have if the roots of this polynomial equation are all real and distinct, are different, then we can see a general solution to be C1, so C1, C2 up to Cn are still some real numbers. E to the R1x, C2 E to the R2x. Still same as before, right? A linear combination. So if each one, think about the R1, R2, up to Rn are some different real numbers. Because they are roots of this polynomial equation, so we say the linear combination is a general solution, right? So just similar as before, but right now we're extended to nth dimension. And to this, right? Because this is our original nth order differential equation. Example. Given these initial conditions, right, up to second derivative, so for this third level differential equations, we want to find a particular solution to this. So again, the characteristic equation is this, right? We have r cubed plus 2r squared minus 3r equals to 0. Because e to the rx can never be 0, so we just skip the step. And the factor r, we have this unfactorable. So we get 3 distinct real number solutions, right? So that means, you know, because of theorem, apply the theorem, the general solution to the third order differential equation is some C1 e to the 0, right, x, some C2 e to the negative 3x, some C3, some constant, C3 e to the 1x. So simplify, we have this. Because we want to solve initial problem, so take y prime first level derivative, we get this. Second level derivative, we get this. Then plug in initial value. Y of 0 equals to 2, we get this equation, C1 plus C2 plus C3 equals to 2. Plug in first order of 0 equals negative 7. Get negative 3C2 plus C3 equals negative 7. Second order plus 0, plug 0, get 5. So that's this. So I have 3 variables, C1, C2, C3. We have 3 equations guaranteed to be solvable. So we solve, yes, in the end, we get a C1 equals to 5, C2 equals to 1, C3 equals -4. So just plug back in C1, C2, C3 for this, C1, C2, C3 for this from the general solution to get a particular solution for the given initial values. Anyone has any question? Yes, Suxian.
Okay, we count like R is 0, -2, 3, and 1, right? So you just said like R1 is 0, R2 is -3, R2 is 1. Can I think like R1 is -3 and R2 is 1 and R3 is 0? Like a,
Of course,
okay.
no
Okay.
problem at all.
Okay, so when we like solve the problem C1, C2, and C3 like same.
Same thing.
Okay.
That's just variables, right?
All right.
You
okay.
can always.
Thank you.
You're
All right.
welcome.
Thanks.
Any other questions? Okay, let's keep going. Second theorem for today. If the characteristic equation has a repeated roots, so this means R, a root have a multiplicity of K, then part of the general solution of the homogeneous differential equation with a constant coefficient is of this form. So this is just for one R, for this R, right? For a particular R. So these roots will be e to the Rx multiplied by some constant plus some constant multiplied by x plus some constant to x squared up to x to k minus 1. Okay, so this is new. This is new to us. All right. So if a root has a multiplicity of k and one of the part of the general solution is in this form, this is a polynomial of k minus 1 degree because the multiplicity is k. If R has multiplicity of 3, you would have a quadratic, right? Second order of polynomial. If k is, think about 5, you would have a polynomial of degree 4. Then to be the coefficient of e to the Rx, right? If k is 5, you would have a polynomial degree 4, then e to the 5x. So this is new to us. Let's see this example. So we want to find a general solution to this. N equals 6. So this is a 6th order differential equation. Right? We have y to the 6th, 6th level differential equation, y for the 5th level, y to the 4th level, right? Equals 0. So the characteristic equation is this. Then we factor r to the 4th. We have this. Then we say r equals 0 is a root. So 0 is a root with multiplicity of 4. And then we have a half as a root as a multiplicity of 2. So according to this theorem, so 1 is order 4, 1 order is 2. So 1 should have the coefficient to be polynomial of degree 3. And this one is a 2 double root, or polynomial of degree 1. Remember before, that's why we say we have C1 plus C2x times e to the 2x. Right now we extended it to k, multiplicity of k. So for this one we have seen, right? Double root we have seen it before, but for the order 4 is new. So for order 4, we have a polynomial of 3, degree 3 to be a coefficient. For order 2, we have a polynomial of degree 1 or linear. Okay, so this is 0, right? So e to 0x, well, with just 1, so we get this polynomial degree 3. E to the half of x, so we get those two. So get those two. So add them all together. That's a general solution. That's a general solution for this 6th order differential equation with 2 roots. One root has multiplicity of 4. One root has multiplicity of 2. Anyone has any question? All right, let's keep moving. So this is saying, okay, what happens when the equation, when the roots of the equation are complex? So like this example, 2nd order of differential equation with a characteristic equation of this, and use quadratic formula, we have 2 complex roots. So complex roots always come in pair, and we call them conjugates. So 1 plus 2i, 1 minus 2i. Right, so R1, 1 plus 2i, R2, 1 minus 2i. It doesn't matter which one you call R1, which one you call R2. So what do? We want to use Euler's formula. Euler's formula is saying e to the ix equals cosine x, real part, plus I sine x, complex part, imaginary part. So for e to the a plus bix, we can write as this, e to the ax, the imaginary part, right? So this is the real part. The imaginary part we write in the form of Euler's formula. Cosine bx plus I sine bx. With this is the minus sign, a minus bi. So the imaginary part we also present with Euler's formula. So if f and g are real value functions, given as this, f of x, capital letter f of x, real part f of x, imaginary part g of x, then we can define f prime of x as real part, the first level derivative of real part, first level of derivative of the imaginary part. Okay, very intuitive. So using this formula, we still can use this formula when R is a complex constant, all right? So suppose a characteristic equation has these complex roots. Then C1 e to the R1x plus C2 e to the R2x will be part of the general solution to the homogeneous equation. And we can write as Euler's formula for the complex part, for the imaginary part. Right, so this one, out of this one, we have e to the ax cosine bx, cosine bx, right? To this one, we have cosine bx, right? C2. So that's why we have this common factor of this cosine bx, e to the ax. So we factor out, we have the e to the ax cosine bx for both C1, C2. Then the imaginary part, we have this sine bx, we have this negative sine bx, right? So that's why we have this I C1 minus C2 with a common factor of those two. So we can write in this case as a general solution for the homogeneous equation. So in general, C1, C2 could be complex constants. So however we're interested in, that's why you guys said, okay, I'm just ignore that. However, we're only interested in the real solutions to the differential equation. So we choose C1 equals C2 equals a half and get only this part as a solution. So we choose C1, C2 Well, one is negative, one is positive conjugates to get this as a solution, right? So e to the ax cosine bx for the real part, and e to the ax sine bx as a solution for the imaginary part. And those two are linearly independent. So again, apply this theorem. I think all of you apply this theorem. If the characteristic equation has a pair of complex conjugate roots of a plus minus bi, then the corresponding part of the general solution of the homogeneous equation is such: e to the ax, real part, multiplied by c1 cosine bx, right, for the plus, c2 sine bx. Right. Okay, example. Second order differential equation given two initial conditions. Characteristic equation r squared minus 2r plus 5. When we solve that, use quadratic formula, we get 1 plus minus 2i. Real part is 1. Right? Imaginary part is 2. So by this theorem, so right away we get this. So we get e to the x c1 cosine 2x plus c2 sine 2x. Sine 2x, okay. Cosine bx sine bx. And the real part is here, e to the ax. In this case, it's just e to the 1x, so the e to the x. Well, we have two initial conditions given. We can solve for a unique solution. So y prime, plug in initial condition for y of 0 equals 3, plug in y prime of 0 equals negative 5. Again, so plug in this, sine 0 is just 0, so get a c1 right away equals 3. The second one, we can plug in c1 to be 3, solve for c2 equals negative 4. So c1, c2 are the only unknowns here. Plug back in, we get a unique solution for given two initial conditions. Anyone has any question? All right, let's see this example. Third order differential equations, right? Homogeneous. And has this one as a particular solution. So this R equals to 2/3, right? So this is R, you can think as R1. R1 equals to 2/3. And find the general solution. So Ryan has presented one, and also Christian presented one something similar to this. So given one solution, so y equals e to the 2x divided by 3 is a solution. So that means a solution, r equals to 2/3. So we have this 3. So we have this equation, right? Characteristic equation or third level polynomial equation. So if this is a solution to this third level polynomial, we could use long division, right? Because that's saying r minus 2/3 equals 0. That's the same as 3r minus 2 equals 0. Right? If we want to use this one, we could use synthetic division. But if we use long division, we use this one. So here we show long division, right? Divided by this. So we get r squared plus 2 as a quotient. So that means this one can be factored as 3r minus 2 times r squared plus 4 equals 0. So this gives us two complex roots, plus minus 2i. this part. So by the theorems, so general solution is the real solution, C1 e to the 2x divided by 3. And the complex part, right? The real part is 0 because it's just 2i. So that means the real part is 0. So by the theorem, we'll have e to the 0x, right? Remember, it's ax, the real part, e to the real part times x. Then C2, because here we use C1, so we use this as C2. Cosine 2x, because b is 2, right? Cosine 2x. And then another real number, we use C3, sine bx, b is 2, sine 2x. So this is a general solution, right? This is a solution for the real part. This is a solution for the complex part. Simplify a little bit, so get this. Anyone has any question? Yes, Shuxian.
When I present you says I need to figure out what like a complex and then a negative one, so I can
No,
so.
because you already know how you already applied theorem, this theorem.
Okay, got you.
Right.
All right.
I was expecting you to write a solution like this.
Oh, okay.
Yeah.
All right. Okay, no problem. Okay, thanks.
Yeah. So you already applied this theorem.
Okay.
Yeah, that's why when I talk to Ryan says, "Oh no, I applied this theorem." Because right, for our class, for this level of differential equations, introduction level, right, we apply this. Okay, any other questions? All right. Okay, now repeat the complex roots, right? When we get the perfect squares. So if a plus bi and a minus bi are roots with multiplicity of k, then the part of general solution corresponding to these roots are of this form. We have the sum of 0 up to k minus 1, same as before, right? But right now, we just have too much to write. That's why we write it in this summation sign. We have xi, this is still like a polynomial part, but multiplied by this real part, e to the ax, then the complex part, right? So those ci, di, just representing some numbers, real numbers. We still have this cosine, this imaginary part, right? Bx and the sine bx. Let's see an example. So this is just very similar to before, right? Just right now, we have complex roots. Let's see this example. So we have fourth order differential equation, like homogeneous equation. Of course, have characteristic equation of such, right? And this, we can factor it as this square. Then with inside, we apply a quadratic formula, so we get 1 plus minus 2i as complex roots. But this roots has a multiplicity of 2. This roots has a multiplicity of 2. So we'll apply this. A multiplicity of 2, so k equals to 2. So we have the e to the 1x, real part is 1, e to the 1x. Then the complex part, we have cosine, because b is 2. We have cosine bx, 2x, multiplied by some real number. Or sine bx, b is 2, multiplied by some real number. Then, because it's a double root, right, multiplicity of 2, so we have this 1 x raised by 1, real part e to the 1x, cosine 2x, right? B is 2, and multiply by some real number, and sine 2x multiplied by some real number. So this is a general solution of that. Anyone has any question? As you can imagine, if this is a 3, right? If this multiplicity is a 3, and we would have a third term, x squared, then e to the 1x, blah, blah. If this is a 4. Yes, Ronald? Ronald, you have a question?
Saying with the minus sign when we're doing the second part where it says x e to the x plus actually c3 close to x plus c4 I think we're supposed to have minus sign maybe. I don't know where.
Oh, okay. Okay, so let's go back to this theorem. Okay, let's right. So I didn't stay enough time for this theorem. So before we would have a plus, we would have minus. We would have both roots, a minus I bi, a plus bi. Right, that's for before. But now we have this theorem. Let's look at this theorem. So this theorem is saying if we have complex conjugate roots a plus bi, and the corresponding part of the general solution of the homogeneous equation is this. You see no more of the minus.
Sign, yeah.
Yeah, we just have e to the ax, real part, solution. And the complex part, we just have cosine bx, multiply some number, and sine bx.
So we just ignore this minus sign, or?
Exactly. We
Okay.
we just apply this theorem.
All right, thank you.
But there's nothing wrong if you still go with this way, okay?
All right, no problem.
Okay, all right. Anyone else have any other questions? And that's it. That's it. That's it for today. So I think most of us are doing great. The rest of you, if you don't present, I have no idea how are you doing in this class. So please try to present, all right? And one way you get presentation grades. And the second way, you show me, how well you are doing in this class. And also, second thing, next class, I would hope some of you turn on your camera so I can see your beautiful face. And then that's all for today. If you have no more questions, you are free bird for tonight. Again, the homework questions are not enough. So what do is you can pick one question and make up your own question. Okay, you just change the numbers. All right. And see you on Thursday if you don't have any questions. If you do have questions, I'm still here. Okay. I'm going to stop recording.